we need something simple to be able to be reassured that we're doing the right thing. If all our theories were so complicated that we didn't feel we can develop an intuition on why things are true, I think it would be very unsatisfactory.
Welcome to the Living Proof podcast. I'm John Farrow, the communications manager here at the Isaac Newton Institute. Every year, we welcome thousands of mathematical scientists to our beautiful chalkboard-filled building in Cambridge so they can collaborate on cutting-edge research. Sometimes they're here for a short time to give a talk or attend a workshop, and sometimes they're here for a long-term program that could have them stay and work here for 6 months at a time. And everyone that passes through our doors has a story to tell. With this podcast, we want to highlight some of those amazing mathematical stories and share our love of mathematics with the world. This episode, we're talking all about chaos, the quantum world, and how time and space are essential for deep thinking. We're joined by Professor Jens Marklof, who is the Henry Overton Wills Professor of Mathematics at the University of Bristol. He's also a Fellow of the Royal Society and was recently the President of the London Mathematical Society. Jens is a mathematical physicist who is interested in understanding exactly how the small-scale interactions described by quantum mechanics lead to the larger-scale phenomena we observe every day. As the Distinguished Rothschild Fellow for the Geometric Spectral Theory program, he's been here at the INI attending seminars, collaborating with colleagues, and recently gave his public lecture celebrating the 100th anniversary of quantum mechanics. Hello, Professor Marklof. Welcome to the Living Proof podcast and to the Isaac Newton Institute. I hope you've been enjoying your stay so far.
I loved it.
So, did you always know that mathematics was for you?
I really loved mathematics at school, as well as physics and other subjects. When I decided what to study, I went for physics because I believed back then it gave me the biggest choice of career opportunities. I studied in Germany, and there's a slight difference between the mathematics degrees versus here in the UK. If you study math, usually there are much fewer students, and it's really already sort of just for the very, very best. And I never felt I was in that cohort. So I went for physics. In the UK, it's the other way around. There's actually a lot of students who are interested in mathematics because they can see that it can lead to really amazing careers. So in Bristol, for instance, we have around 250 to 300 students starting every year in a math degree, and it's similar in many other institutions. So that's a real difference, and I found that very interesting.
So when did you make that switch from physics to mathematics, or did you?
So my undergraduate degree was already very heavy in mathematics. So essentially half of what we're doing were lectures delivered by mathematicians. And I think I got a really solid, rigorous training in pure and applied mathematics back then. And then when I decided what to do for my master's thesis, I was really attracted to work with the professor, that's Frank Steiner, who taught me quite a few lectures in theoretical mathematical physics in Hamburg, and he was a leading expert in quantum chaos. So then my thesis was on arithmetic quantum chaos, which was already very, very mathematical. And then I had the great luck to meet on my very first conference as an undergraduate student, Peter Sarnak from Princeton, who I noticed was flicking through my undergraduate thesis in one of the lectures. And I took all my courage to talk to him afterwards. And so we started talking. And at the end of the conference, I asked him if I could go and work with him in Princeton for a year. And he said yes. So he was a mathematician. And then I went to Princeton to work with him there. And what I then really realized that some of the top mathematicians like him have a geometric intuition that's very, very similar to how physicists think. What I learned there, then in addition, that you also have these amazing tools that allow you to turn your intuition into rigorous proofs. And that I found really fascinating, rewarding, and I knew then that that's what I wanted to do.
I guess at the boundary then between mathematics and physics.
That's right. So the really exciting thing in quantum chaos was that there were lots of open problems, questions raised by physicists. And then you had absolutely fantastic world-leading mathematicians who were working in analysis, number theory in particular, who could transform those questions and conjectures by physicists into mathematical problems that were relevant in their subject area. So, for example, in quantum chaos, a really beautiful connection was made between the distribution of the zeros of the Riemann zeta function. The proof of the Riemann hypothesis is one of the big outstanding problems. And the observation that the statistics of those Riemann zeros could be modeled by random matrix theory, just as the eigenvalues of quantum chaotic systems could be modeled by random matrix theory, was a huge stimulation to this collaboration between mathematicians and physicists. So that was very exciting. And similarly, also other phenomena like apparent randomness of quantum eigenstates in chaotic systems had a connection with L functions. That's something that Peter Sarnak brought out and made really important contributions. So it was very exciting to make that bridge between physical conjectures and really pure mathematical models where you initially wouldn't think they have any physical meaning, but actually they do. And you could use then those techniques in pure mathematics to answer in those models the questions that physicists had raised.
Thinking about the Isaac Newton Institute, then you sort of memorably came here in 1997 for a program. Can you tell me a bit about that experience and what it was like to come back, 29 years later?
I had finished my PhD, so the stint in Princeton was a year in my PhD. I then went back to Germany to finish my thesis, and while I was finishing my thesis, I was at a conference in Germany, and we went for a hike with all the participants, and as we were on top of the hill that was sort of the objective of that hike, John Keating came to me and said, "So Jens, what's your plan now for after your PhD?" And I said, "I have no idea." And he said, "Would you like to come to Bristol? I have money for 4 months." And I said, "Sure." And he was one of the organizers of the Newton Institute program, which would happen exactly after those 4 months. So he said, "You come to Bristol and then we'll try to get you some money to also attend the Newton Institute program." So I had 10 months then basically, and I applied for funding. I was extremely lucky to get it. This was the European Postdoctoral Institute program, which then also allowed me to spend 18 months in Paris at the IHES, also one of the leading research institutes in mathematics in the world. So I was extremely lucky to get that, and I think that really set me off.
So the program was on disordered systems and quantum chaos. Seems, exactly right in your wheelhouse. But it featured some of the same people that are here now on our geometric spectral theory program. So you and John Keating, Uzi Smolanski was there. It's not obvious to me why those two fields should have so much overlap. Can you explain what disordered systems and geometric spectral theory have to do with each other?
Yes, absolutely. So disordered systems are systems that are really important in solid-state physics, understanding conductivity of material. Led to several Nobel Prizes. Anderson localization, for example, is one of the really amazing phenomena that were predicted by Anderson. And that happens when your material is not a regular crystal, but a regular crystal with random impurities. And what these random impurities do is they create insulator. And it is really a fantastic sort of observation that Anderson made that then led to a whole sort of subject area developing. And that was the first part. That's a disordered system. And then quantum chaos is a system that's actually not disordered. It's a very simple system like the ones I showed in my Rothschild lecture. It's a particle moving in a billiard domain, and the chaos here is just created by the shape of that domain. So there is no randomness in it, or the pseudo-randomness, maybe one should say, comes through the fact that the underlying classical dynamics is chaotic. and then would like to understand how the corresponding quantum particle behaves and how chaos emerges there. So these are the two topics, disordered systems and quantum chaos, that were covered in this 1997 program. And how is it connected to the 2026 program that we have now on geometric spectral theory? Well, geometric spectral theory is the mathematical theory that deals with analyzing such systems like the quantum particle in a domain, or the quantum particle on a hyperbolic surface. So these are, again, mathematical models. I mentioned it earlier. In arithmetic quantum chaos, there are arithmetic surfaces that have beautiful arithmetic structures. So these are then mathematical models for quantum chaos. And the conjectures, some of the conjectures that were made in the late 70s, early 80s, that were really at the core of the 1997 program, are still relevant today, and we're still trying hard to find ways of understanding those rigorously, but even heuristically. It's still a mystery how these phenomena can be explained.
Does the similarities come down a little bit to sort of shape and geometry, that the reason why the systems are disordered or the quantum systems are chaotic has to do with the sort of shapes and geometry involved, and then you're sort of analyzing
Exactly.
it?
And you see, if we think of the three words, geometric, spectral, theory. So spectral, quantum systems are characterized by their spectrum, right? If you look at the spectral lines of helium or hydrogen, those come from the quantized energy levels of the system. And so geometry stands for, we analyze the connection between the geometry and the spectra of our mathematical models. So that's really the connection. And quantum systems are one example of spectra that you can get. Other examples are you bang a drum, right? And what Schrödinger really developed, his wave mechanics, basically means that a lot of quantum systems have physical analogs. So, for instance, a quantum particle moving in a flat domain has the same spectrum as the drum of that domain. So if you have a classic circular drum, the resonances of that drum are exactly the same as the quantum energy levels of a quantum particle confined to a circular domain. So that's the connection. That's why there's no quantum in the title of the current program, but, certainly quantum systems are a subset of the kind of things that have been discussed here.
In your talk, you talked a lot about people or even other mathematicians, they sort of need a basis from which to understand new ideas. So there's the idea of planetary orbits led to the ideas about electron orbits. Wave equations were easier to grasp than matrices, so that sort of became the more popular theory. But with quantum mechanics, and honestly, sort of a lot of advanced mathematics, this connection to something like graspable is really hard. So how do you just give up and you sort of not link it to something sort of known and sort of forge out into the unknown, or do you keep trying to find that kind of graspable?
Let me just clarify one thing you said. So historically, matrices were a novel thing, and people didn't like the idea of Heisenberg's absolutely ingenious paper because it was so mysterious on what was going on there. And then when Schrödinger came with the wave equation, suddenly they were relieved because, studying wave equations was 19th century mathematics. We knew a lot about wave equations then. So from a historical point of view, today matrices are everywhere. Everyone loves matrices. So it's really changed. Matrices, linear algebra are at the very heart of machine learning algorithms. So they are absolutely there. Everyone has to learn about matrices today. Okay, so that's really changed. It was a historical, really remarkable sort of occurrence of how the psychology of the scientists at the time, sort of their reaction to this revolutionary paper that Heisenberg had written.
But then I guess, once something becomes very useful, then more people start to learn about it and use it, apply it in their different fields, and now and then it becomes everywhere.
So the power of mathematics, physics, and other sciences, chemistry, and so on, is that you develop models that explain somehow the things that we can't imagine, right? We have to remember that quantum particles, atoms, electrons, live on length scales that are 10 to the 10 times smaller than our experience. So they're completely different. And nevertheless, we always cling to this idea that things should be similar, that, electrons should behave like planets flying around the sun. And we still have this sort of vision, and then we overlay that with our mathematical interpretation, which allows us to make predictions and test those theories. But it's still kind of an interesting thing, and on how we get used to those abstract concepts. And I think it is exactly the same how we get used to living in our real world. We don't understand why the sun, certainly as a small child, while the sun sets every day. And we get used to it, and we're not questioning it, right? And then, of course, we look for explanations, and we come up with beautiful theories. But I think that experience of developing a model, testing it, and then at some point just accepting that that's the reality. That's how science has been so incredibly successful. And I think the idea that you can take something very complicated, break it down into smaller, simpler things, develop abstract theories, and abstraction means simplifying. That's the whole point. So we understand now all these little patches. We don't understand the whole picture yet. I mean, we would love to unify all physical theories. One of the holy grails is to really understand how we can unify quantum theory and Einstein's theory of gravitation. That's still unclear, but that's our desire. Maybe it'll never work, but our desire is always to find something common denominator that just makes everything look much, much simpler. I think the real difficulties that scientists had at 100 years ago when modern quantum mechanics was developed, I think today we're a little more used to it. And, we see those pictures of individual atoms. And so it just gives us a feeling, yes, it's like that. And we can make very accurate predictions, right? And we can test those, and we get the right results, mostly. So that gives you some reassurance.
There's the famous Isaac Newton quote about standing on the shoulders of giants. If I can see further, it's because I'm standing on the shoulders of giants. And your lecture really, I thought brought that home. You were talking about these, amazing discoveries from 100 years ago, and then your own sort of contributions to that. How much do you feel like that's a central part of how mathematics is done?
Mathematics, of course, builds on what people discovered earlier. The mathematics is an amazing human construct. And I just feel so humble and looking back on these amazing tools, theorems that were proved even 100 years ago or more, that are still today absolutely stunning, and that we built on. I mentioned in my own research, of course, I benefit from the amazing insights that physicists had in formulating these big conjectures in quantum chaos. I mentioned the Berry-Tabor conjecture, and also the conjecture by Bohigas, Giannoni, and Schmidt. Actually, Berry is, of course, in Bristol, and Bohigas, Giannoni, and Schmidt were in the lab in France where I did my second postdoc. So I really appreciate that and feel very lucky. I really benefited from these insights. At the same time, also, my biggest achievements, I would say, as a mathematician, were to use incredibly powerful machinery that was developed by Dani, by Margulis, and in particular by Marina Ratner, her measure classification theorem is, in my view, one of the most important mathematical achievements, certainly of the second half of the 20th century. And I've been using it all the time to prove my things. So I've taken those conjectures in physics, study them in certain mathematical models, which allows the application of those very sophisticated techniques in ergodic theory. And so I was also fortunate enough to tell Marina Ratner that on her birthday conference in Jerusalem some years ago. And I was very happy to say that her theorem determined my career, basically.
No, that's amazing. Thinking about your own time here at the Isaac Newton Institute, did you get a chance to interact with some younger, earlier career researchers and sort of be that Ratner or Thouless for the next generation?
Well, I'll never be a Ratner or anyone that famous for the next generation, but of course the Newton Institute is a great place for collaboration, for interaction without hierarchy. So I think the great thing, what I experienced back then in 97, and which I think is still true today, is that early career researchers from, PhD students to postdocs to people who've just started their lectureship feel able to just approach anyone who's there. I think the architecture of the institute is really good because you see, as you step out of your office, you see who else is around. You have a really good view who's discussing on the blackboards. And so it really, I think, facilitates this interaction. And people are here, of course, they don't have teaching obligations while they're here, so they're free to discuss. Lots of seminars, but most importantly, lots of free time to talk. And I hope that the people who are now early on in their career got something out of talking to me. I certainly get something out of talking to them, because the great thing about mathematics somehow is that you are not necessarily at your peak when you're older. You might have more experience, you might know more about the literature, and that's sometimes an obstacle, know more about all the things that haven't worked in the past. Whereas if you're young, you actually come in with lots of fresh new ideas, and more senior people like me actually benefit a lot from talking to early career researchers who have new perspectives, who are willing to take more risks in their research and explore new ideas and areas. So I think it's a two-way thing here. It's not just that I'm giving them all my knowledge. No, it's often the other way around. So I benefit a lot. And that's why I enjoy actually talking to everyone who's got great ideas.
So, I mean, one of the things that happens here is you come and stay for a long time. You have that time and space to think. I was really struck in your talk you talked about how both Heisenberg and Schrödinger, were basically struggling with health issues and went away from their normal lives, and then for a month or two, and then they sort of came back with these amazing discoveries that went on to change the world. So yeah, how important is that time and space to collaborate and to make progress on difficult problems?
Yes, it's absolutely critical. And what I would say is that you can't have that all the time. So it's actually good for you to teach, to have other things, as did Heisenberg and Schrödinger. I mean, Heisenberg had just finished his PhD, so he's been probably very busy writing up his thesis and preparing for his defense, which he almost failed. And Schrödinger, again, he was older, and he had duties, lecturing duties, and so on. Interestingly, he was asked to give a course about de Broglie's new theorem on the particle wave sort of duality, and I think that triggered something in him. So it's good, I think, to have other things that keep you busy, but then you need, I think, that space and time where you can absolutely dive deep into the subject. And I also felt this myself. And the important thing that you are able to create that absolute concentration for you. So what I did sometimes, which something that worked to me, is to come to a place like the Newton Institute or to go and visit a collaborator, but really also just have time for myself, because some things you can only discover by complete concentration. And I feel that in today's world, there's a lot of distraction. But the ability to say for a week, and that's, I think, Heisenberg's and Schrödinger's situation, for a week to completely forget about everything else but the thought that you want to pursue. And it doesn't always work, but it sometimes works. And if it works once or twice or 3 times in your career to achieve something absolutely remarkable and outstanding, that is a success.
One of the things that I found very interesting was you said that randomness at at a small scale is the thing that actually is what makes larger scale things predictable. Can you explain that sort of counterintuitive connection?
So that's a beautiful idea that goes back to Boltzmann and Maxwell in the second half of the 19th century. Here the big challenge was to explain the laws of thermodynamics, fluid mechanics. How do things move? Can we explain the wave equations that governs ocean waves, for example, through Newton's laws of motion, of the individual molecules that make up matter? At that time, we didn't have quantum mechanics. We didn't even know whether matter is made up of molecules. That was an assumption. And in fact, Boltzmann was ridiculed for that idea. People thought of, water as a continuum, not something made out of microscopic particles. So Boltzmann's big idea was to say that I model my molecules, say my water molecules, as little round spheres that bounce off of each other. And when 2 spheres collide, that can be explained by Newton's laws of motion. It's quite simple. But then you have many of those, and they collide many, many times. Now, each collision introduces sensitive dependence on initial conditions, because these spheres are sort of convex. So if you change the initial angle of collision slightly, then the angle after the collision will have doubled. So if this happens n times, you get an error of 2 to the n, which increases exponentially in n. And so what Boltzmann understood is that this microscopic chaos actually leads to a very beautiful partial differential equation, something we call today the Boltzmann equation, which then can be used to take another step and derive the equations of fluid dynamics, the famous Navier-Stokes equations, for instance. So this has been an open problem for over 150 years, and there's been some quite spectacular progress recently to establish these steps rigorously. People have been working on this continuously since then. So that's the idea. The microscopic chaos allows you to, things start averaging out, a bit like in the law of large numbers. If you just repeat sort of independent coin tosses many, many times, you can then predict the frequency on how often you get heads or tails. And if it's an unbiased coin toss, it should be half of the time. So it's a little bit like this. You have all these independent chaotic events that happen on the microscopic level, and they all start averaging out in a really good way, which then allows you to predict how the wave would move that is made up of these small particles.
If those collisions weren't chaotic, so if, for example, I don't know what shape they would have to be, but if they all reflected very easily and nicely, would the final product be as predictable?
It would be completely different, and it would be very, very predictable, and it would lead to a completely different world that we would be living in. In fact, it would be horrible, because there is something good about the molecule sort of doing something random, because the sort of bad things that could happen become extremely unlikely. Whereas if you have a so-called integrable or pseudo-integrable system, the system essentially moves in a very predictable way. So if you set off in a very unfortunate way, that'll just stay very unfortunate, and it's good sort of that our microscopic world is chaotic. It's a really good thing.
A few times in our conversation, you've described different equations as sort of beautiful and amazing, and I mean, there's a bit of aesthetics here, isn't there? Like, what to you makes a beautiful equation?
It's simplicity, and the point of mathematical equations is that they can be very, very simple, but can have extremely complicated solutions. So a big breakthrough in, our understanding of the world is that we shouldn't just try to write down the solutions of those equations all the time, because they can be very, very complicated and varied and appear in many different forms and shapes. No, we have to write down those equations. So that's something that I guess goes back to Newton and people before, which is that the equations are the simple thing and the solutions might be very, very complicated. And so you could have an equation that describes a lot of different phenomena. And the difference in the phenomena that it describes just comes from the fact that you have different initial conditions that you need to use in your equation and so on. And there are many mathematical equations where we can't write down the solution, but we can look at the equation. So that's the point. They're simple. They're easy to remember, and they give us a feeling that we understand the world around us, even if we don't, because we can't solve those equations.
Why should the world be sort of simple and elegant, even though the equation feels beautiful and nice and complete? Why do we expect that the world will follow that?
No, that's a great question. And the point is that our world is not simple. It's very, very complicated. And there are many things we don't understand in this world, right? It is always the hope that you can reduce explaining the phenomena that we see through very simple equations. And it is this reductionist approach that has been very, very successful. And where complexity theory and chaos theory really come in is when you then try to really put all those different equations back together and try to explain really complicated things, like our atmosphere and the weather and so on. But the amazing thing is those simple equations still sort of work. Some we can't solve. We need a supercomputer to predict the weather because we can't solve the equations for the weather analytically. But it just works. And that's the beauty of it. And it comes back to my initial point, is that we need something simple to be able to be reassured that we're doing the right thing. If all our theories were so complicated that we didn't feel we can develop an intuition on why things are true, I think it would be very unsatisfactory. And, with all the AI and so on, what I always say is that, well, that's at least my view, is that AI can explain some things to us, but it can also create a lot of noise, untruth. And unless we understand the results that we are being given by our favorite large language model, unless we develop an intuition and a reassurance that what we're being given is actually true and correct, it will be useless. So that's where simplicity comes in. It gives you reassurance that you're on the right track.
You mentioned AI. It was really interesting. Looking back at that annual report in 1997, the other program that was here at the same time was on machine learning.
Yeah.
And Geoffrey Hinton was one of the organizers who went on to win the Nobel Prize more recently. So you were sharing an office with David Thouless, who went on to win in 2016, and then Geoffrey Hinton was presumably just down the hall. Is that just like a normal Tuesday for the Isaac Newton Institute, or was there something special, that year?
Well, I think it's a pretty amazing track record for the Isaac Newton Institute to have hosted two future Nobel Prize winners at the same time. I mean, it means, the selection of programs were really topical, high class. And I think looking back at the programs that were hosted here, these were all frontier research programs, coming in at the right time. I mean, the challenge here is, I guess, you decide which programs to host, and then there is, 2 years until they actually come together. So you really have to take your bets and predict, what area will be, topical and so on. So I don't know. I think it'd be great for the Newton Institute to actually have a little look on their record and how many future Nobel Prize winners were hosted here. But it's not just about the Nobel Prize winners. It's about just the people who have emerged from here, who've done other amazing things and won other major awards. And I'm sure the Newton Institute has a great track record. I don't have a recollection of Geoffrey Hinton. I might have gone to some of the public lectures back then. I know some of my PhD sort of student friends, they were getting interested in this neural network stuff and so on. And I sort of looked at it and I thought, oh, this will never take off. This is how wrong I was. Yeah. So it's quite amazing to see this. And of course, having shared an office with David Thouless was an experience. And in particular, and I've seen this with many, many superstar scientists that became my role model, is that they were humble, they were not arrogant, and it was always about the science.
If you could go back in time to 1997, and say something to your past self to sort of set you in maybe in a different direction or the same direction, or whatever, if you could give advice to yourself back in 1997, what would you say?
I have to say I've been really enormously lucky in my career, and I also, looking back, I mean, of course I was less mature, I just started off, but the thing that the advice that I had given myself back then was, I think, advice I would give myself again, which is to have a plan B. You can never predict whether your career will go in the direction that you hope. And what really helped me is to have a plan B, namely to say, okay, if this doesn't work out, I'm going to do something else. I'm going to, go into industry so I had a plan, and that helped me because it helped me relax and really take risks, which you have to do in research. You can't just do mediocre things if you want to have a good career. You have to take risks, explore new and original ideas, and go your way.
Is a mathematical career chaotic? Is it sort of dependent on, very sensitive on initial conditions?
That's a great question. To some extent, yes. You, of course, benefit from the education you get, from your parents supporting you. Some people don't have that support, and that stimulates them too. But I certainly would say that I benefited from great parents who gave me really good advice, especially early on when my studies didn't go so well. And yes, it is chaotic. And, the people I've met along the way, so I mentioned earlier this meeting with Peter Sarnak, but also other people I've met, which look like random events, right? And I feel very, very lucky. So that element of chance. However, it's also a question of then recognizing the opportunity that you have and really grabbing it. And so I think it's a combination. And as with the small water molecules bouncing off of each other in chaotic ways, you want to move the probabilities in your favor. So do things about how you can create good opportunities for you by grabbing those chances that you have.
I think that's a great place to leave it. Thank you so much for a great conversation.
Thanks, John.
If you love maths and can't resist a good puzzle, you're going to love this. G Research, the quantitative research and technology firm, has a brand new monthly series of mathematical riddles designed for people who enjoy thinking deeply. Every month, the riddles get a little tougher, and if you crack them, you'll be in with a chance to win cash prizes. It's free to enter, fun to try, and perfect for anyone who likes stretching their brain. So if you're ready for a challenge, head to gresearch.com/riddles and check out this month's puzzle. That's gresearch.com/riddles. Go give it a try. Thank you, Jens, for a fantastic conversation. I learned a lot about the quantum world, about how a mathematical career evolves, and why chaos isn't as scary as it might sound. And thank you for listening. If you enjoyed the podcast, please make sure you subscribe to get notifications when the next episode is out. Until then, see you next time on Living Proof, the podcast of the Isaac Newton Institute for Mathematical Sciences.